Who's here in town during spring break? A lot of people. Who's leaving town? Okay, it's kind of curious. It's quiet in here. We have fewer than 100 people out of 1,600 people. So we're touching almost 5% here. That's pretty fun. What's that? Yeah, I'm going to go to Chicago to go visit my wife's parents. And then we're going to go to Point Reyes on the weekend. Not this coming weekend, but the next one. I've never been there somehow. Yeah, I know. I spent 15 years here. It's pretty far, though. It's like almost 2 hours away. Anyway, all right. Hi, spring break friends. Okay, so I think who's done after this class? It becomes spring break then. Okay, cool. A lot of people. Great. All right, well, I'll launch you. That'll be on the webcast. Good. So a reminder, not just to you, but the webcast. We are going to be running the full autograder on 4.2 so we can get grades out. So, of course, because there's no autograder that you can use, that means we're not going to accept extensions beyond that. So if you have something insane that happens, then let me know personally. In terms of the extension system, just a quick note. So I really enjoyed the extension system. It was an experiment born of I would like people to catch up if they're behind, and I would like people to feel less stress. And the trade-off, of course, is, well, if the extension system is a little flexible, then people will abuse it. So it took a while for people to start abusing it a lot. But 2A, there's just a lot of people starting on Friday, and office hours still had people working on 2A 3 days after it's due. So we're going to be tweaking it in some way yet to be decided, but just be aware. It's going to be stricter. All right. Other thing is, you notice Wednesday, I mean, you guys are here in person, so probably you didn't notice this, but I did not pre-record the Wednesday lectures. Just a little too busy. Same this time. So this will be after this week, I'll be back to the lectures that are at my house. So, shortest paths. All right. Before we get going on this problem of trying to find driving directions, I want to reflect on what we did at the last lecture where we had DFS and BFS. Yes, question. Sorry.
For this up to, what is the
Last lecture of the midterm? I don't remember. Let's look. It could be, I think it might be Monday. Let's find out. I can't. It'll be the Monday after. Yeah.
Okay.
Yeah. So today's in scope. So is Monday. Okay. I'll try and get that one up as soon as possible if you want to do it over spring break. All right. So basically, we got DFS and BFS as our two ways of exploring graphs. And you might ask yourself, well, if we have two ways to do the exact same task, is one of them better? So let's think about possible differences. One of them is correctness. So will both of them work for all graphs if our goal is just to find any path? The answer is, in fact, yes. Doesn't matter which one you use. It'll give you the right answer. It'll give you an answer. That is, it will give you a set of paths. In terms of output quality, is one better than the other in some way? I don't know. What do you think? Is the output of DFS or BFS for paths better than the other in any way? Yeah. Yeah. BFS, those ones are shorter. So if you care about shortness, I mean, BFS, you can think of it as a 2-for-1 deal. You get paths, and you also get the fact that they're the shortest. How about time efficiency? Is one more efficient than the other? Well, we know they're both big O of V plus E, and that's the hard thing that you'll take some time to digest from the previous lecture. But they should have pretty similar runtimes, and my kind of hokey argument is we consider all the edges twice, so probably it'll be close. With the BFS, you have to have a Q. Who knows? You'd have to do some very careful analysis or do some kind of experiments. All right. How about space efficiency? Is one more efficient than the other? Well, I'm just going to drop this on you. DFS, it turns out, is worse if you have a spindly graph that's long, like a linked list, because it'll have a very deep call stack. That is, the computer will have to keep track of all the calls that were made. Now, this is a 61C topic. We never really talked about this. But basically, the computer needs to know where it came from so that when you are returning from DFS 12, it needs to know where to return to if the previous call was DFS 11. It needs to keep track of that somewhere. And so it would need theta v memory in the worst case. BFS, by contrast, it would be bad for bushy graphs, so for space. So imagine that we have a graph where all of the vertices are connected, and you start from some source. Well, then you're going to enqueue all of the other vertices at once, and that'll take theta v memory. Now, this isn't necessarily such a big deal because in our implementations, we are already using theta v memory for those distance to and edge to arrays. So it's not changing the order of growth of the memory, but it is possible to change your implementations so that you're only storing dist2 and edge2 in some kind of map instead of an array, and maybe that saves you some space. This is kind of an outside point, not very important. I'm going to keep moving. So what's better, BFS or DFS? I think the short answer is neither of them is better. The only real critical difference that we've seen is that BFS gives you shortest paths. Okay. So we asked this question, which was, would BFS be good for a driving, like Google Maps? And the answer is no. And we mentioned it was because not all roads are the same length. And so I have a quick example. This is just some place in the world. Here's a source, here's a target, and you want to get there. Now, if you're very keen-eyed, you'll notice that these names are in Chinese, and it's because I took this from my own Chinese language version of this class. Here, let's go to it. It's kind of fun. Okay, my Chinese students, you guys know about Yodao, I bet. Yeah. Oh, yeah, nice. So anyway, you can look me up. Let's see. I'm going to log in as me. I can't read Chinese, by the way, so I just know this from muscle memory. All right. So this is just a side gig. It was a small thing. I didn't design a whole course. I just helped them design a class and gave some guest lectures. So let's see. Where's me? Okay. Oh, yeah, there it is. This is the data structures class that I helped build. And they have a description. Okay. They Photoshop me a little. There's me. Anyway. Anyway. And this is Anderson, also known as Being. But anyway, he's good. Anyway, so if you want to watch these class done in Chinese, you can do that too. But it's a little different. It's in Python too. Anyway, all kinds of linguistic changes. Anyway, so having taught that over the summer a little bit, I created some slides, and I took this one because I thought it was fun. So I want to get from this location somewhere in Beijing to this other place. And so you might ask yourself, what would be the corresponding graph? Well, it would be this graph. It would have a vertex for every intersection and an edge for every connection between intersections. Now, if we use BFS, we might not get the right answer. So in particular, BFS, if you go from this source to this target, it would find a total distance of 190, whereas the correct result is you should go in a straight line instead of going over here for no reason. So why is BFS taking this bad path? Yeah. Yeah, you only got 3 edges, and that's not what we want. Okay. So if we want to do driving directions or any similar problem, we're going to have to do something smarter, and our goal is to do this, to take into account our edge weights. Okay, any question about the setting of the day? So far we've said DFS and BFS are equally good. BFS gives better paths, but if you want to take into weights, you need something better. Yes. Yes, so here I really care that this is 110. So the algorithm we're going to conduct should ultimately take into account these distances. Yeah. Alrighty. So, Dijkstra's algorithm. That's what we're going to invent. And I'm going to start by making you find the shortest path from some S, so in this case 0, to this vertex V. And you can think of this as road length. And, if you're going through the mountains, the roads are windy. So even though it's a straight line, the actual road's windy, and it's actually 15 units of distance. So what I'd like you to do is find the shortest path the ultimate goal will be the shortest path from S to T. You're going to go from 0 to 5. Okay, so try and figure out what the shortest path is, just by eye. Okay, so you've thought about it, and even if you don't have it yet, this is the correct shortest path. Okay, total length, if these are miles, would be 9 miles. You could use this link instead, which is 16 miles, but that's too far. Okay, all right. So how do you do it? Well, you guys did it by some kind of optimization procedure where you're like, well, that seems pretty good. Oh wait, this road's pretty long. So we're going to kind of emulate that process. And before we get to any kind of algorithm, though, I want to show you that we can solve an even more general problem. So an observation I'll make first before we talk about this more general problem is that the solution we just came up with will be a path that has no cycles in it. And why is that? Why are there no cycles guaranteed? You'll look here and you'll see there's no cycles. But why would I never have a cycle in driving directions? Yeah. Just don't do it. Like when someone's like, okay, let's get to Dallas and then drive in a big circle back to Dallas and then continue on. Just don't do that step. Okay? So you can always cut out the cycle. And so it's always going to be a path Now, if you have negative weights, then it gets complicated, because then maybe you want to take the cycle, because you're taking less and less time the more times you take the cycle. And that's the thing. In financial modeling, something known as arbitrage is equivalent to the problem of finding negative cycles in a graph. It's beyond the scope of our class, though. Okay, so now let's think about a different problem, which is what is the shortest path from the source to every other vertex? Not just 5, which I'm showing here, but I want the shortest path to every vertex. And this one I'm going to give you a minute or so to think about what the solution would even look like. Okay? So in other words, there's 6 different targets you need to consider. 1, 2, 3, 4, 5, and 6. And I'd like you to think about what the solution is. Like, what is that object? What does the answer feel or look like? So I'll give you guys a minute to ponder that. You don't have to come up with an algorithm, by the way. You just have to figure out what the answer is. Okay, I'm going to spoil it. So, the correct answer, kind of interestingly, is that you don't have to write out 6 different lists of things that you need to do. That is, you don't need 6 different edge 2 arrays, one for the path to 1, one for the path to 2, and so forth. You don't need to write down 6 different paths. In fact, the solution for all targets is a tree. That is, that if I go from 0 to all paths, right, this tree basically, this node has 2 children, 2 and 1. And then 1 has 1 child, 4, and 4 has 2 children, 5 and 6 has 1 child, 3. And you could think of this as the union of all those different shortest paths into one tree. And it's guaranteed to always be a tree. Because the shortest way to get to 6, for example, is going to be the shortest way to get to 4 plus a single vertex, right? So to get to anywhere, you have to get somewhere else first. And this is a subtle philosophical point. It took me a while when I first taught this class to sink in. But the answer will always be a tree. Yes?
How would you store the distance from node? Because yes, you have the number of nodes. How would you store the
So if you wanted to know the distance from 1 to 6, for example, you could not just store it in a distance to array. You'd have to specify a source and a target. But here's the key point. We have a single source and many targets. Okay? So this distance to array represents only the distance from the source. The total distance to 3 is 11, because we go, let's see, 3, where's 3 at? Oh, up there, yeah. 2 plus 3 plus 5 plus 1 is 11. Okay? Yeah. This is only true for directed graphs. Let's see. That's an interesting question. So if you have an undirected graph, then what is different? Do you always have a tree? Yes, it is also still a tree. And the way you would show it is here you take every directed edge and you just make a copy of it going the other way. That's the equivalent of an undirected graph. And so it also turns out to be true, though. Yeah. Okay. And the reason I'm doing directed, I forgot to mention this earlier. You might say, why are we doing directed all of a sudden? It's just that it's a little more general. If you think about directed, it's easy to think about. But all these results hold for an undirected graph. The only thing you need to do is take each undirected edge and then make 2 edges out of it. So we'd have an edge from 6 to 5 and an edge from 5 to 6. Okay. There's no difference. So the key punchline here, and the very important point, and something that people learn Dijkstra's algorithm, and you may say to yourself, why am I bothering going to college and just instead of watching some random YouTube video about Dijkstra's, where they explain this whole thing in 8 minutes instead of 50 minutes. And it's that I want you to understand these really important underlying points, like that the solution is always a tree. That's an elusive point, but a very important one. All right. So this Yell key link is broken, so don't use it. So a question for you, and I'll only give you that long on this one. Let's say that G is a connected graph. That is, you can reach every vertex from the source. Maybe I shouldn't have said connected, but let's say that all vertices are reachable from the source. This is an old slide. I don't know how. This is a minor terminology issue, but it's bothering me. But I'll just say it's connected. Whatever. All right. So let's say that you can reach anything from the source, And let's say in total there are V vertices and E edges. How many edges are there in the shortest paths tree? Okay, let's assume every vertex is reachable. So here's an example where we have 7 vertices and 12 edges. Okay, so first question is, how many edges are in this shortest paths tree? 6. Okay, let's say we have V vertices. How many edges will there be? V minus 1. This is kind of a cute one. Why is that? Well, because for every vertex, there's always going to be exactly one input edge. That is the way you get there. So to get to 3, you have to come from somewhere. 6. To get to 6, you have to come somewhere. 4, and so forth. So that's the argument. So for another way of looking at it that's maybe more obvious is just that if we look at our dist2 and edge2 array, all entries but the source are filled in. Okay? Cool. So goodness. How do we... Oh, yeah, go ahead. Is that true for any tree? Let's see. Yeah, any tree. Any tree of V vertices has V minus 1 edges. Sure. Yeah. Good. All right. All right. So, one more time. I want you to, I know we already did a shortest paths tree problem, but I want you to do another one, because this one we're going to do many different ways. So I just want you to do this one by hand just to familiarize yourself with the graph. Your goal is to find the shortest paths tree, which should have how many edges? You have 4 vertices, so you need 3 edges. Okay, find your 3 edges. You only get 25 seconds. Okay, here's the answer. So the answer is you go from A to C to B to D. That is the shortest paths tree. In this case, it happens to be a line. That's okay. Sometimes that happens. So the purple line numbers are annotating the total distance from the source. So the source is 0 away from itself, 1 from A, 2 from B, and 4. D is 4 from, sorry. C is 1 from A, B is 2 from A, and D is 4 from A. Jeez. All right. You got it. Okay. So how would we find the answer? Well, what we're going to do first is I'll give you an example of a bad algorithm. And this bad algorithm, actually I'm going to do 2 bad algorithms, then 1 good algorithm. So whenever we start, this is the starting state of the graph. So all the vertices are unmarked, all the distances are infinite, and there are no edges in the shortest paths tree. That's where we begin. Okay? So the first algorithm I'm going to propose will be something very similar to depth first paths. I'm just lazy. Like, if I tried to write anything, I'm just going to make up one bad idea, which is, let's do depth first search. And then when I visit a vertex, that means any outgoing edge that is not part of the shortest paths tree, any vertex I can see that is not already part of the family, that is not already pointed to by the shortest paths tree, I'm going to add the appropriate edge. This algorithm will not work, but it is just something we could code up. Okay? So, for example, I call DFS on A, and so that means I'm visiting A. And then I'm going to say I have 2 outgoing edges. Well, is B in the shortest paths tree? No. Is C in the shortest paths tree? No. So I'm going to add those edges. Okay, I update these distances, and now we keep going. Now, the difference between this and what you guys did is you're humans. You can reason and kind of backtrack and look at it and think about it in all kinds of ways. But this is a very dumb algorithm that does no thinking at all. So now I have DFS of B. That's next. Why? Because it's depth first search, and the next thing in my adjacency list from A is B. So when I do DFS of B, I look at its outgoing edges. So first of all, if I look at the edge from B to A, well, I see that A is already in the shortest paths tree, so I'm not going to add that one. But here, D is not. So I'm going to add it. And at this point, because of the way that my algorithm works, I'm never going to add any more edges, but we'll keep running it. And so next step, who am I going to DFS next? Let's see. Is that actually the right answer? If it's DFS, I think it would be D next, right? Yeah. So it would be D next. Wow. See, another bug in my slide. Oh, I know why. Let's just change this color. Man. All right. Everything will be fine, guys. All right. Okay. Talking out loud is very different than running through at a faster pace than normal. You realize the errors. So next you'd call DFS-D. It has no outgoing edges, so there's nothing to do. And then after that, we'd have DFS-C. When we get to C, it has 2 outgoing edges, but the targets are already in the shortest paths tree. Okay? Now this shortest paths tree is wrong, but this is what it tried to build. Okay? So I didn't like that algorithm very much. So I'm going to propose a pretty obvious idea, which is let's say we were looking at this DFS call. So when we are up here, when we were looking at DFS of C, we refused to use this edge, right? We said no, because it's already in the tree. But should we have used it? What do you think? Why? Shorter. 1 plus 1 is 2, and 2 is less than 5. 1 plus 5 is 6, and 6 is less than 7. Okay? That's the idea that I'm going to bring into play with my next algorithm. Okay? So bad algorithm 2 is going to be, let's do the same thing. We'll do depth first, but this time we're going to add the edge if the edge gives us better distance. So instead of it being, are you part of the family, it's, are you a better member of the family? And if so, I'm going to get rid of whoever was there before. Okay? It's more brutal, but it will give us better answers. So this time, the way DFSA works is we say A to B has distance 5, which is better than infinity, much better. So let's use that. And A to C is 1, which is better than infinity. Okay, next step, DFS of B. Well, B to D has total distance what? 7, okay? 7's better than infinity, so we'll replace that. How about, what's the distance we compute here, back to A? 8. 8 is worse than 0, so don't use that one. Okay? One more. So we do DFS D, nothing happens. We'll fix the color on the slide. Okay, it's okay. It'll be fixed on the next one, though. It's only these 2 slides. Okay, I made a better example, but I screwed up one thing in the process. All right, here we go. So next we have DFS of C. Okay, so in this case, C, we do, what's the distance we compute looking at B? It's 1 plus 1, like we did out loud. And is 2 better than 5? Yes. So we replace it. And over here, 1 plus 5 is 6, so we'll replace the 7. So 2 things. One, the term I'm going to use for this process of calculating this number and then using it if it is better, I will use the word relaxation. That's a weird verb. In this case, it's a transitive verb. I'm going to relax this edge. And it comes from the idea, there's probably, there's no rubber bands, but that's kind of one here. No, okay, that's a fragment of a rubber band. So if you stretch a rubber band and then you let go of it, it like snaps to its appropriate size. So that's the metaphor here. Like this, if you like let this edge go, what happens? Okay, that's a weird term, but that's just what they use. Okay, so using an edge if it's better is called relaxation. 2, is the shortest path tree correct? No. Okay, what's kind of like philosophically, what's the problem? Like if we wanted to fix it, what would we do next? Yeah. Well, it doesn't have to be a direct path, actually. This could be the shortest path tree. It could be correct if these values were different. Like, let's say this 5 said 0. This would still be the correct shortest path tree. Yeah. Yeah, you'd have to go back to B. So B was marked, and now we'd have to go back to B. And that's a valid algorithm, but it's slower. So there's a better approach, and that will give us what is known as Dijkstra's algorithm. So there is a variant of this, which is just if you happen to visit an edge, if you happen to update someone's distance, you have to revisit them, like unmark them. That will work, but it'll be slow compared to this other way. Okay? This alternate cooler way is Dijkstra's algorithm, invented by Dijkstra, who I guess I'll talk about in a later lecture, but he's a very interesting guy. So his approach is, instead of doing depth first, do best first. And this is your first taste of CS 188. You're going to do so much best first stuff in that class if you take it. The idea is you want to go to the closest vertex possible first, and when you visit, you'll do the exact same thing. So the algorithm begins exactly as before. You'll notice there's no difference here, except that the reason we start with A is that it has the shortest distance. So A is the closest thing to A, so we're going to use it first. Now at this point, what is the closest vertex? Is it B, C, or D? C. Because it has distance 1. Okay, great. So let's do that. We go DFS on C. At this point, 1 plus 1 is 2, which is better than 5, the old one. So notice that this edge 2 value has shifted. And now we don't have that danger of needing to revisit b, because we haven't even been to b yet, right? And then over here, we have 1 plus 5 is 6, better than infinity. So who are we going to DFS next, b or d? B. So we go to b last. In this case, when we do DFS of b, we consider the edge back to a, which has total weight 2 plus 3 is 5. 5 is worse than 0. So we don't want to do this loop thing. And then the other case, we have our other edge coming out. 2 plus 2 is 4, which is better than 6. Okay? So there's two changes we made. One is relax your edges instead of just using them. And 2 is go best first. And this is guaranteed to be correct. Okay? Yeah. So if a to b is 2, yeah. 2, 11, 20. Yeah. Are you saying, will it work still? It will definitely still work, but it's a little too much for me to put out just verbally. So I would encourage you to try it later, but I think that we're likely to lose a minute in the class without a lot of elucidation. All right. Okay. Let's do a bigger example. That one was too small. Okay, that's a good question. We'll come back to it. 2, 11, 12, or definitely think about it later. And anybody webcasting, you can try it out and see what happens. So here's how you might actually implement this. So the original Dijkstra's algorithm did not use a priority queue, but typically in a modern implementation you do. Okay? Because it's the easy way to keep track of which vertex is lowest or closest. So the approach, the Dijkstra's version I'm going to describe is you start by putting everything in the priority queue and giving it distance infinity or priority infinity, and then the source is going to just be our starting place. Okay? Equivalently, you can insert the source with priority 0, but I decided to do it this way. So when we start, okay, all the distance 2's are infinity, the edge 2's are blank, and we have these two edges. Okay, what are these two distances going to become? 2 and 1. Okay, that one's pretty easy. So that means we update our distance 2, our edge 2, and we do 2 change priority operations. Change priority, that sounds familiar. Okay? You guys did that one. 2a. Okay. So you know how that works. You know it should be log time. Okay? You've built the data structure needed for this. It's almost as if homework 4, you're going to build this using your data structure from 2a. Woo! Anyway, all right. Okay. Who's next? Yeah. Oh, yeah, we're going to give you a staff solution in case your project 2a is broken. So don't worry if you didn't get 2a working right. All right. Or if you're worried about bugs you didn't find. So the fringe now has, remember the fringe term from before, by the way. I didn't say it again, but the fringe is the edge of what we're exploring. Okay, so who's going to get DQ'd? Who has the lowest priority? 2, which has priority 1. So we'll go there next. It has 1 outgoing edge. What will 5's new distance be? So it's infinity right now. 16. Okay, because it's the distance to 2 plus this edge. We update the priority, we update distance 2, we update edge 2. Okay? When we do a relaxation operation, what's the total time to relax an edge? Well, distance, that's a good question. So I got a constant time vote. What else? Log. So how long does it take to update this array entry? Constant. How long to update this? How long to update the priority? Depends on your priority queue, I guess. But the way you guys did it, it would be log. Okay. So in a typical priority queue, it'll be log. So relaxation is a log time operation because we have to do a change priority. Okay. So what happens next to you guys? We got to DQ another vertex. So which one's it going to be? 1. It has 3 outgoing edges. Oops. Of these, well, the bottom one, this one's not, or the leftmost one's not used because this would be 7. That's worse than 1. This right here would be 5, better than infinity. This is 13, better than infinity. Okay? Which vertex is next? 4. Good. Okay. So now a question for you. What changes? I just want to make sure. If you understand this, you understand Dijkstra's algorithm completely. So row 2, row 5, and row 6 are the ones you need to consider. Spoiler. Okay, any questions about my answer versus yours? And if you get this, you understand all of Dijkstra's algorithm. Yeah. Say again? Why both? Why do you change both at the same time? It's just how our algorithm works. We relax all edges. That's what it means to visit a vertex. Relax all outgoing edges. Yeah. Oh, it'll work for both directed and undirected. Yeah, I'm just doing a directed case. Yeah.
So to make sure I'm clear here, the priority queue starts completely filled with all of those.
Correct. Yes, nothing in my version of Dijkstra's is ever added. There are other versions, but this version is everything's up front. In homework 4, you will not do that. So the downside of putting everything in advance is that if the graph is very, very big, you can't fit it in your computer. So you will be solving problems that are too big to fit in your computer's memory at once. On homework 4, so you won't do it this way. But it's a minor tweak, and I'll describe it in great detail. Because it's a homework, so I don't expect you to be designing it yourself. Yeah. Why do we remove from the fringe? The fringe basically tells us the following. Which vertex is closest? And we always want to do the closest vertex first. That's why. So it's our way of keeping track of who's closest to the source. Alrighty. Okay, then we keep going. Blah, blah, blah. All right. Now, one thing I guess I should mention, the very last one that happens, vertex 3, it's going to do a relaxation operation. And something I didn't say earlier is that any edge pointing at a white or already visited vertex, those relaxations will always fail. Okay, and I'm going to revisit this again. But I just want to say it first now, and I'll say it many more times. But this I already know, just looking at the figure, I don't have to do the adding. I see an edge pointing at a white vertex. I know that the relaxation is not going to yield a better answer. What I just said is why Dijkstra's works. Okay, we're going to go into that in more detail now, though, so don't sweat it. Okay, so let's talk about why Dijkstra's works. So now at this point, I hope that you all understand exactly what it is. Here it is in pseudocode. So Dijkstra's one version. You start by adding the source and giving it priority 0. You add all the other vertices with an infinite priority. Then as long as the queue is not empty, you're going to say, P, you are the smallest vertex that exists. Like I'm removing you. Then I'm going to relax all of P's outgoing edges. And then what does relaxation mean? Well, that means for each edge, if the distance to P, for each edge that goes from P to Q, if the distance to P plus W is less than the distance to Q, that is like the pink number plus the black number is less than the old magenta pink number, at that point, that means I need to do some things. First, I need to update the distance, and then I need to set its edge 2 value, and then I need to set its priority, the thing that I'm pointing at. Okay, that's the whole algorithm. And to me, having taught this class a lot of times, it feels like this small. For you, it's probably a little bigger. But if you think about this, this will eventually seem like the most obvious thing all around. All right. So what are some properties or invariants of this algorithm? First of all, what are each of the variables? So edge 2 represents the best known predecessor of V. Like how do you get to 5? The best way is coming from 4. Dist 2 is always going to be the best known total distance from the source to V. And then the priority queue, very importantly, it keeps all of the unvisited vertices in the order of distance to. Okay? You don't actually need the priority queue. You could just iterate over these 2 variables, but it's faster. Instead of iterating over your whole array to find the closest thing, like in Dijkstra's original paper, a priority queue speeds things up a little. Some important properties. 1, this will always visit the vertices in order of total distance from the source. And secondly, whenever you relax an edge that is already visited, it will always fail. Okay? That's the second time I said it. Okay? Right. There's a lot to take in here, though. Okay? Yeah. Mm-hmm. Well, I don't want to go through the whole algorithm again, but I'll leave it to you guys to think about in some more detail. Okay, so Dijkstra's algorithm. If you wanted the one-sentence version of it, it's you visit the vertices in order of best known distance from source, and what visitation means is relaxing all the edges from the visited vertex. All variants of Dijkstra's algorithm will match this description. They'll do it in slightly different ways. Okay? And furthermore, it's guaranteed to give you the best result possible if the edges are non-negative. So why does it work? Okay, I'm just going to give kind of a proof sketch, but the fact that this work relies on that property that relaxation always fails on edges to visited vertices. Okay, so basically it starts like this. It's an inductive proof. So at the start, I hope you all agree with me that the source has distance 0, and that's optimal. There's no better way to get to the source, right, than just being there. So then, after you relax all of the edges from the source, so you have vertex 0 and all of those edges coming out of it, let's say vertex V1 is the vertex that's closest. It's like the thing after those first relaxations that's closest. So I'm going to claim that the distance to the smallest vertex. Here, I'm going to give you a specific example. I think it'll be easier to see. So when we first do these two relaxations, which one's going to be closer? Vertex 1 or 2? 2. I am claiming that vertex 2 is optimal. Okay? Why is it optimal? Well, the reason it's optimal is that all future relaxations on it will fail. And the reason is, let's think about this. Let's say that we're looking at a future relaxation operation. Okay? P, let's say P is something that comes later, like vertex 6 or 7 or whatever, and it has an edge back to 1. Well, the distance just to that vertex is already bigger than the distance to 1. So therefore, if I add weight to that distance, it's always going to be bigger. Maybe if I just show you this figure again, it'll be easier to see. So the distance here is 1. All of these other vertices will have a distance greater than 1. You agree with that? Or greater than or equal to 1. And therefore, if you add their distance to some weight, that's still going to be bigger than 1. Okay? So that's why it works. Because all of the vertices come later in the queue, and the only thing they could possibly do is add yet even more weight to get us to this starting vertex, or this situation where V1 is 2. Okay? It's not a hard proof, but it's probably a little hard the way I described it to fully grok. And you can basically just inductively show that if that's true for V1, it's true for all. Okay? Yeah. Yeah, so for negative weights, there are a few algorithms. If the graph has no cycles, you can just relax. You can visit the vertices in if there's no cycles, you visit them in basically like a breadth first tree order. So there's no cycles, you start at the source and you just do a level order traversal of the tree, relaxing as you go. If there are cycles, then you can use something known as Bellman-Ford. And this is the algorithm. It's very silly. It's for every vertex, relax all the edges, do that V times, and that will work. So, yeah. There's other intermediate algorithms. Yeah. If you want the optional Princeton textbook, does talk about those other two. Yeah. So a negative weight could represent, for example, let's see. So it could be that if I'm doing, the currency trading is the example I remember seeing. It's basically, when does it come up in currency? I'm trying to remember. What's that? Yeah, so whenever you're trying to convert between currencies, yeah. So it's basically if I'm going from this one to this one, it's, what does the number represent between the two currencies, though? Oh, I see. So it's like a 0.5 up and a negative 0.5 going the other way, something like that? Yeah, something like that. Other examples of negative weights. I mean, it could just be, what are some really natural examples that come up in this class ever? I don't know. Good question. So currency trading is the one I had in mind, yeah. Ah, yeah. Yeah, so if you want to do something like trying to track elevation, then it's some other slightly different problem. It's interesting to speculate about what that might be. So after we do Project 2C, we'll come back to that. I'd like to talk about that in lecture. Yeah. Yeah. Yeah, so traffic maps are very complex because the weight of each edge dynamically changes. So how you could do it, I think, I'm just speculating, I've never worked on it, but I think what happens is that each edge is weighted by the time needed to traverse it, and then everybody's phones are reporting those times, and so the weights of the graph are shifting over time. All right. Now, I do want to mention this about negative edges. Sorry my lame answer about what negative edges might mean, but I'll try and think of one as I'm talking. So the reason negative edges causes things to fail, and this gives you some intuition for why the proof is true, is that if you have negative edges, then even though vertex number 33, which has distance 82, has already been visited, if later I visit vertex 34 and relax this edge, I find a new, better path, which is to actually go and take this negative edge. Okay? So relaxation of already visited vertices can succeed. Dijkstra's fails. You have to use Bellman-Ford or something else. Okay. All right. What about its runtime? I'm going to do the runtime of Dijkstra's in 30 seconds because it's actually very easy. So if we look at the pseudocode, there's nothing in it except basically priority queue operations. So or at least that are interesting, because everything else is constant time. So the priority queue operations, we start by adding v vertices, and each will cost log v time. Big O log v. So the total adding cost is v log v. Removing smallest, well, there's v vertices, and we're going to do it v times, and each one's going to cost big O of log v. The later ones will be a little cheaper, but whatever. Like overall, it'll be certainly bounded above by log v. So the total time for all the remove operations is v log v. Okay, more than 30 seconds, I lied. And then the change priority operations, for every edge, that is the worst possible case, is that every single change priority operation happens. That would be the worst thing that could happen. So that would be e change priority operations, each costing log v time. So the overall time for the algorithm would be the total of all adds, all removes, all changes. So that'd be v log v plus v log v plus e log v. Now, assuming that e is bigger than v, which is common because that means you have at least as many edges as vertices, you can summarize it as e log v. Okay? But you could also write it as v plus e parentheses log v if you don't like that. Okay? So the overall runtime is e log v. Any questions? Yeah. Typically, you'll have more edges, actually, than vertices. So if we look at these figures, just to get a typical picture, it would be something like this. So I have, because if you have one edge per vertex, at least. Remember, the E is not per vertex. It's the total in the whole graph. That's the key. Yep. All right. Okay, good. All righty. So I got some good news and some bad news. We have a pretty good distance finding algorithm, but things are a little strange. Okay. So let's say we are trying to do Dijkstra's algorithm to get from Denver to New York City. So first question. Assuming that the map is good, okay, like that all the distances are fine, will Dijkstra's give us the shortest path? Yes. The answer is, in fact, yes. Will Dijkstra's algorithm explore the space in an efficient manner? No. Why? That's kind of a vague question. What is something that Dijkstra's will do that seems weird? So it's visiting things in the order of distance from Denver. So it's going to kind of explore outwards. So it's going to find, yeah. Sure. Yeah, it goes to Dallas. Why are you going to Dallas? Doesn't make any sense. So it's going to explore every place within nearly 2,000 miles of Denver. It's going to go everywhere and find New York. It'll terminate, but not as fast as it could. So if we only had a single target in mind, instead of all targets, we need a different algorithm. So how do we do better? Well, we want to try and do some kind of eastward thing first. We want to bias the algorithm in an eastward direction. So here's where we're going to get a little bit of a 188 preview. Okay. So I'm going to tell you about A star. A star is so simple, there's almost nothing to say compared to Dijkstra's. But instead of doing distance from Denver to V, this would be best first, or closest first, I'm instead now going to add an estimate of the distance from V to the goal. So as I'm visiting vertices, I'm not going to care just about how far I am from Denver, but also my best guess as to how far the vertex that I'm thinking about is to the goal. Okay? So let's take Denver, for example. We could go to Broomfield, Henderson, Inglewood, or Aurora, just roughly speaking. So Henderson, it is farther than Inglewood. This line is shorter than this one. However, Henderson's in the right direction. And so if we add the estimate from Inglewood to New York and if we add the distance to Inglewood to the distance to Inglewood to New York, that gives us one value to consider. And in the other case, we'd say, what's the distance from Denver to Henderson plus the distance from Henderson to New York? And in that case, we're going to say the Henderson direction seems a little better. Okay? It's really so simple, it's almost confusing, as I like to say sometimes. All right, here's A star running. Just to show you there's almost nothing to it. So in this case, my estimates of the distance from V to the goal, all I've done is I have written down the size of the smallest edge out of a vertex. Okay, so out of 2, the smallest edge coming out is 15. That's my crappy estimate of the distance to the goal. In this case, the goal is 6. So it's an underestimate, right? But it's my best guess. All right. So if we run this algorithm, Same thing. Start with all infinities, all that stuff. And now, when I relax these edges, I am, instead of ordering them by their number, their literal purple number, 1 and 2, I'm going to add to 1 what value? Nope. 15. Why 15? Because that's my estimate of the distance from 2 to the goal. Where did this number come from? I have no idea. Someone made it up. Doesn't matter. Some arbitrary constants. Okay? So in this case, 2 actually gets the value 16. And 1, what are we adding to its distance of 2? 3. And why? Because it's in the table. That's it. Okay? And I haven't told you anything about where these numbers come from. Let's just say you had them. Okay? So who comes next? 1 or 2? All right, we did 1 this time. That's different than before. Remember in the previous example, we went to 2 first. Now we're going to 1 first. And the reason is that Dijkstra's wasn't exploring in the right direction. Like, 1 is a better bet because it has these small edges coming out of it. 2 is kind of, it's got this giant mountain road after it. I'm worried. That's too far. I don't want to deal with that. Okay? So next up, 2, we relax all of its outgoing edges. Okay, so this is the same process. Actually, what's this infinity going to turn into? 5, okay? It will be 5. So the distance is still recorded as 5. However, what will be the priority of vertex 4? It'll be 5 plus what? Which is 11. There it is. So literally the only difference between this and before is the weighting in the fringe, but the distance 2 and edge 2 stuff works exactly the same. Okay? Any questions about that? Yeah. Why? Well, the rough, and I'll leave this as an exercise if you want to do it later. The rough reason is that if you watch how this algorithm, like if I just do the next so many steps, which have nothing new to them, at this point, I'm actually going to be totally done once I've only visited these 3 vertices. That's why. Okay? So at this point, I'm done. I've found the shortest path to 6. It is 0 to 1 to 4 to 6. Okay? Now, there's a couple things I want to notice. 1 is not every vertex got visited. And 2, the result is no longer a valid shortest paths tree. So, for example, the path that I have given to 3 is not correct. But we didn't care about 3. That wasn't part of our goal. Our goal was just to find 6. So the only path that's guaranteed to be right is the path to 6. Okay? Now this is, if it feels a little queasy, that's fine. This is AI. Like this is your first AI lesson, which is that instead of exploring the whole space exhaustively, we're using a best guess to guide our search. And it gives us an answer that's a little weird, but it gives us the correct answer for the one thing that we actually care about. Okay? So I think that's pretty cool. All right, so that's A star. And so an important question is, well, where the hell did those numbers come from? Well, okay, so that thing, that function, that estimate is known as a heuristic, and it's just some arbitrary function. And heuristic, by the way, is an English word meaning using experience to learn and improve. It doesn't have to be perfect, and in fact, it's impossible for it to be perfect. So let's give an example of a heuristic. For this map, what can we use? If you wanted a heuristic for how far it is from Inglewood to New York, you don't know the actual distance because there's all these windy roads between Inglewood and New York, and you haven't looked at all of them. So what could you use as just a guess? Yeah. Coordinates, sure. Then what? Like latitude and longitude, then what do you do with that? Yeah, what's your estimate, though? Yeah, go ahead. I'm cutting you off. Go. Yeah, you just measure like the straight line distance, the great circle distance over the Earth. You imagine the tunnel if you dug them between the city, whatever you want. So you have some function that computes, I don't know, I'll call it the linear distance or the line distance. I give it the latitude, longitude of V and my goal. And this is an underestimate because in the real world, I'm going to have to follow some windy roads instead of flying. Okay? That's basically how it goes. Now let me show you a quick picture of how Dijkstra's and A star compare. So I'm going to put a wall between green and purple, and I'm going to use Dijkstra's algorithm and show you how Dijkstra searches. So you'll notice it's searching in a big circle. It's not so good. Okay? It's like, yeah, it's kind of Pac-Man-esque. Found it. So it finds the correct answer. It just takes forever. A star, by contrast, it expands, but it does something a little smarter. It's making better choices. Okay? So that's what you're going to be building on homework 4. So let me just give you a very quick preview in the spring break of A star heuristics. So is A star guaranteed to be correct? So I'm going to do it. I'm going to keep you extra 30 seconds than usual. So let's say you just say the heuristic that everything is distance 10,000 miles. What will A star do? Dijkstra's, because then you're adding a constant to all the values. Nothing happens, okay? So if you just pick 0 or 10,000, you just get Dijkstra's. So bad heuristics can be fine. What about if you say don't go to Illinois or Indiana, and you say these are all distance 100,000 because I don't want to go to the Midwest? Will A star give us the right answer to New York City? No, and the reason is that the correct answer goes through Illinois and Indiana. So how do we know if a heuristic's good or not? This is your 188 preview. If your heuristic has these two properties, admissibility and consistency, which I will not even say out loud what they are, but they're on the slide if you're curious. Take 188 if you want to know. As long as your heuristic has these two properties, A star is guaranteed to be correct. I will never ask you about this. All you need to know is that the choice of heuristic matters and that a bad choice can be bad. Okay? But if you really want to get into that, that's 188. But this is more of a data structures class than an AI class. Now, just by the way, turns out that all consistent heuristics are admissible, and all admissible heuristics do give you the correct route. With a certain version of A star. We have a Venn diagram. But you know what I'm going to do? I just really don't want to go into this because this is like, solid 10 or 15 minutes of proving. So 188 will go into this in some more detail. So just to summarize, if you want to get from one place to another, Dijkstra's is one way to do it. A star is a better way. If you want to get from one place to all other places, you should use Dijkstra's. That's it for today. If you got any little questions, I'm happy to take them up front. And have a good spring break. Thank you, folks.